Hello, in this video we will be seeing how to find the minimum path sum in a m by n grid matrix, and the problem statement is that you will start at the top left corner and you want to reach the bottom right corner, which is our end goal, and we have to find the minimum path sum. The path sum is going to be from the cost associated with the path that we try to take. So let's say we took this path. The cost is the cost associated with each node aggregated. So this node has a cost of 1, then this node has a cost of 3, this has a cost of 1, 1 and 1. So this becomes 1 plus 3 plus 1 plus 1 plus 1, which is given us 3 plus 4, 5, 6, 7 as our problem statement here. And the problem statement also says that you have to follow a set of rules when you try to find this minimum path sum. These rules are: you can either go in the right direction from a specific position in the matrix, or you can go in the down position. So you either go right or you go down. What this means is that if I start at this point in the matrix, I can keep going in this direction, which is the right direction, or I can keep going in the down direction here. And this is what I have to follow throughout the problem statement. I cannot, if I reach here, I cannot say I will now move left or I will move on the top. I have to keep going right, or I have to keep going down, or I keep doing a combination of going in the right direction and then going down and then again going right. But the aim is still that you start from here and you have to reach here. And we will build a solution in JavaScript, and we will also compute the time complexity and space complexity of the solution that we will be building in JavaScript. Now, we said that we will be trying to solve this using dynamic programming here. What this means is we're going to have some subproblems. We will solve these subproblems and then we will reach a final solution that we are looking for. Whenever it comes to dynamic programming, the format that we can keep in mind in terms of the approach that we try to solve a problem statement in is that first, form a base case that we will be using. Then from this base case, you try to create a expression which will repeat, and then you reach your final solution by repeating this expression that we build. And this expression is going to be a subproblem that we try to solve. Now, the aim here is to find our smallest subproblem that we can solve, and then we will keep on expanding the scope of our subproblem to reach the final solution. What that will mean is, let's say you start here and I'm saying that, okay, I want to reach from here to here itself. So from this node, I want to reach this node itself. This can be my smallest subproblem. Or I can say, let's expand the scope of my subproblem a bit, and I'm going to reach from here to here, and this is going to be my subproblem. Or I can say I want to reach from here to here, and I can say this is my subproblem. Or I can say this is going to be my subproblem that I want to solve, start from here and want to reach here. The aim is to take the smallest subproblem, and the identification part of this smallest subproblem is the most trickiest part in any dynamic programming solution that we try to achieve. Once you are able to identify this pattern, then it becomes a bit easier to tackle the solution aspect of it. And this can most often be quite tricky to try to get this subproblem pattern. In this problem statement, what we can do is, let's try to start with the smallest subproblem itself. So let's say for a base case, I want to reach from this point to this point. What is going to be my path sum? The path sum is the cost of that node itself. So I want to start here, I want to reach here, which is going to be in my grid, and I will get some solution. Now this solution I will store in some state, and then I will keep a track of the solutions in the state itself and try to use it to solve the next subproblem. So I will keep solving my smaller subproblems, and then I will try to use the state of these smaller subproblems and reach my grand solution. That's what the goal here is going to be. And what we will do now here is that, let's say I wanted to reach here. I will store everything in a array, which is going to be my 2D array as solutions, and then I will use that and find the final solution. So for the first problem statement, which is dp of 0, 0, which is, so let's say we will maintain an exact 2D array of solutions, and for the first solution we said dp, which is going to be my solution array, is going to be grid of 0, 0, which was 1 in this case. This is my base case, which I said is the foundation of the problem's solution. Now I will expand this base case slowly in the possible ways that we have, and try to reach a final solution. Now when I say what possible ways we have, we said that we can either go in the right direction or we can go in the down direction. Now let us try to consider a smaller sub-statement with a bigger scope. Now what I will say is, I want to reach from this point to this point itself. So I will start here and I want to reach here at this point. So this is going to be my final point in the matrix which I want to reach. So the first statement, the problem statement, said that the smallest one, which was from here, I want to reach here itself. Now I will say from here I want to reach here, and that will translate into code something like this. So please note that this is 0, 1, 2, 0, 1, 2, and this is translating into 0, 1. So the 0th row and the first column that we are looking for. And we said we will put all our solutions in our DP array, which is going to be the 2D array that we maintain. And I will say DP of 0, 1 is going to be something. Now in our first case, the solution was the cost of the point itself. Now in our second case, we will just expand this a bit. So I will say DP of this is going to be, we take into consideration the cost of this node, which is 3 in this case. So I will say take this 3, and if I say I can go from this to this point, is it possible? I said I can go in the right direction or I can go in the down direction. Now if I go from here to here, this is going in the right direction. So this is possible to go, but I cannot go from here to here, considering that I just have this as my problem statement right now. Nothing else exists apart from these two values in the matrix. So I will just say 3 plus 1, which will translate into code as, the value is of grid of 0, 1 plus my previous solution. Now please note that what I mean by previous solution is, I will take into consideration the cost that it took me to reach this point, and then add my current point cost to it to say that I have reached my solution. So the previous node, which was this one, what was the cost? The cost was stored here in my base case step, which was dp of 0, 0. And that's pretty much it. So we have 3 and 1 giving us 4. That's what we were looking for. Now we will proceed ahead and let's try to find, are there any other possibilities which could have become our next smaller subproblem. We said we could go in the right direction, so we went from here to here and we considered this as one of our subproblem. Now the problem statement also says that you can go in the down direction. So now what I will say is, instead of this two values, I can say that I want to go from this node to this node because I can go down. So I will say I want to consider just this two in my matrix. Nothing else exists, only these two values exist. Find the cost to reach from here to this point. That will translate into something like this. This point is in the matrix 0th column and the first row. This is dp of 1, 0. Now let's follow the similar pattern that we followed. You start from the base case and then you try to reach your solution. So the cost of this one is 1, which is translating into grid of 1, 0 plus what is my previous node that is being considered into this matrix. Now we said only these two elements exist in the matrix. So to reach here, you take the cost of this one and the cost solution of this one. So what was the solution of this point to reach this point? In this case, it was a base case solution, which was 1, that just translates into code as dp of 0, 0. So this is what we were looking for as our base case that we wanted to solve. So this is another possibility that we could follow. Now we covered the aspect of base case, we covered the aspect of creating a repeated expression for a smaller subproblem up to this two and this two. Now what I will do is I will expand the scope of my smaller subproblem. So at first I considered this two, then I considered this two. Now I will say I want to consider this 4 that I have. And my goal is to start at this point and I want to reach this point in the matrix. And how do I achieve that? Let's follow the same pattern again. I will say dp of 1, 1, which is the representation of this one, is going to be the cost of that point itself, which in this case is 5. And that translates into grid of 1, 1 plus something. Now in the previous statements we said the previous statement was this one, the cost of itself plus the solution of the previous one, which was 1 in this case. And here we said for the second problem statement, from here to here, the cost is going to be the cost of this one plus the solution to reach this point, which translates into this 2. Now to reach this point, I can either come from the top like this, or I can come from the left, because we say you can either go in the right direction or you can go down. In the first two use cases that we saw, there was nothing on the top on this side because this was our first column in the row. So like did not have anything on the top here. This was our first, and this was also our first. So first column, and this was our first row. So we did not have anything coming from the top for this one, and for this one we did not have anything coming on the left hand side. But now to reach this point, I can either come from the top side or I can come from the left side. So which one do I pick? We go back to the basics of this problem. The problem is minimum path sum. So we have to find the minimum of these two possibilities that we have, which will translate into code as give me minimum of the top one. Now the top one will translate into something like this. So in visual representation, the top one is dp of 0, 1, which is going to be this one, and the left one is going to be 1, 0, which is basically this one that we are looking for in the matrix. So the one that we have here, and then you have this possibility also. So this two, and the minimum of those two that we have is going to be the one that we pick up to try to reach our solution. Now the value of my previous case, which was 1, 0, is 2. So minimum of this one is 2, the value which was found here, and dp of 0, 1 is going to be 4, and the minimum of this 2 is of course 2, as we have here, and then we add this 2, which gives us 5 plus 2 equal to 7. This is a repeated pattern that we try to see. So first we covered the edge cases. So you just wanted something on the borders. On this border, that is our first column, and on this border, which is our first row that we try to solve. And then we tried to expand our problem statement a bit, and we said I want to reach this point. What is going to be the cost that is going to be associated to reach this point, which we computed here. And this becomes a smaller sub-problem now. Now we found a smaller sub-problem. Now let's just try to create an expression out of it, which we will then repeat. This will translate into something like this. So to reach this solution, what did we do? So dp of I, j, let's say I, j was this one, was basically the value of the cost that was associated with the node itself, which is inside a grid, plus it was the minimum of my previous solutions from the top and the left side, which basically translates into dp of I minus 1, j, dp of I, j minus 1. So the top one and the left one that we have. And this is the expression that we said we are looking for, with which we will try to reach our solution. And that's pretty much it. Now we will just repeat this and find our solution, hopefully. Let's go from the start now. We said we will have a base case, we will have this expression, We will repeat this, have our subproblems, store our solutions in this TP array, which is going to be a 2D array, and then finally have my solution using this repeated expression of my subproblem. That's just what we're going to do now in code sense. So what we will do is, I will now go and say declare a DP array. So I will say let DP is equal to new array of something. Now we have a grid which is going to have a number of rows and a number of columns. So let's say let m, which is going to be my number of rows, be grid dot length. The input that we receive will be in array format. So we will receive an array of input, and then from that we have to just return a number in the problem statement. So this is going to be the input format, and then at the end you will just return your minimum path sum that we are looking for. And let's say I want to know the number of columns. I can just pick any row. Let's say I pick my first row and I try to find the length of my first row. That will just give me the number of columns which we have in the matrix that we are looking for. So this is going to be rows, and this is going to be my columns that I'm going to be having, that we will be trying to solve a problem statement with now. And we said we will be having a DP array that we will be using, and this will just translate into something like this. So you create up to m elements in the array, then you just fill it, and then you create your 2D array. And to do that, you can just do within this array you map and you create a new array of n, which is the number of columns, and then you just fill it with zeros for now. We will keep on filling this 2D array to reach our final solution, and to make things simpler I have just pre-fill it with zeros for now, and then we will keep overriding these values with the solutions that we have. And then in the end what I will do is I will just say return dp of m-1 comma dp of n-1. This is going to be my last node that we have, that we try to store our solution in, which is represented by dp of m-1 comma n-1, considering we have m rows and n columns. Now comes the logic part. We said that we will have a base case at the start, which was initializing the first smallest subproblem's solution. So this smallest subproblem has a solution of this one. So that will translate into something like this. So dp of 0, 0, that is the solution of our base case, the trigger case, which we often solve manually, then extrapolate it, is just going to be represented into something like this. So we covered our base case. Now let's go to the expression part of it. And we said in the expression part of it, we will repeat it. And to repeat, we will just use a loop. So I will say, I will use a iterator. Let's say I will iterate all the rows using a loop here. Then I will iterate all the columns also using a loop. So this will take care of my repeat aspect of my problem statement solution here. And then we said we have this solution expressions that we build in this problem solution. So we said for the first topmost row, for the first topmost column, and then other nodes in the matrix that we have. And the expression that it translated into was represented by this grid of I comma j plus the minimum of dp of my I minus 1, which is my top node, and dp of I comma j minus 1, which is my left node that we had. And this will translate into something like this. dp of I comma j is going to be, so I will first write the expression of this one, grid of I comma j plus grid is going to be storing all our costs that we have associated with this matrix, and then we are going to have math.minimum of dp of my top most node, which is going to be I minus 1 comma j, and we are going to have the leftmost node, which is going to be I comma j minus 1. So this is a expression which we covered here. Now let's also try to cover these two aspects that we wrote. So this was the topmost row and this was the topmost column. Now let's say we said if we were at the topmost row, which is this in this case, you cannot really go on the top more further saying I minus 1, because then it will be 0 minus 1, which is minus 1, which is undefined. So there is no point going out of bounds. Similarly, if you are on the first column, you cannot go j minus 1 for the first column further because you are already at 0. So 0 minus 1 is minus 1, which is going to be undefined out of bound that we will get. So we need to handle the topmost row and the first column use case also, and those will be something like this. So this is topmost row and the first column, because you cannot go on the left if it's the first column any further, because there is nothing, that is the starting point itself. And I will just tweak the expression a bit for both these use cases. So I had this one. If it is the topmost row, I said I cannot go on the left, on the top anymore, because you're already on the top. You cannot go any further on the top. You could go on the left side if you are not at the top, the first column, but you cannot go on the top anymore, which will translate into just this. I'm not able to go on the top. Whatever I have on the left, I will just pick it up. Similarly here, I cannot go on the left. Whatever I have on the top, I will just pick it up. So these are my cases. With these cases, we will try to build a solution now. And for these cases to be suited properly, I have to put some checks in place, and the checks will look something like this. So for the use case wherein you are not on the topmost row or the first column, it's going to be I is going to be greater than 0 and j is also going to be greater than 0. In that case, this use case suits us perfectly, which we covered earlier. And then if I is greater than 0, which means that you are not on the first row that you have, for that case you will be able to go towards the top side because you are not at the extreme end. And similarly, if j is greater than 0, then you can go on the left side. So these are the cases that we covered, and this is how it translates into code. We initialize our base condition. We have number of rows, number of columns. We filled our DP array. We use the base condition value here for a trigger, and then we just went through our loop, and then you just, in the first loop, it will use this value of DP of 0, 0 solution that we have in our main case, and then we will just try to find a solution. If we had not initialized this one, if you see, everywhere we are checking either both of them are greater than 0 or one of them is greater than 0. So if we had not put a trigger condition, we would not have got our initial cost of the top left, the minimum path sum of that one. Hence we have to trigger a minimum path base condition like this in this specific problem. And that's pretty much the solution that we were looking for. And then if I just try to run this problem, I will see that the test case that we had initially kept passing. So that's pretty much our solution. In terms of space complexity, we maintain this 2D array which is filled like based on the number of rows and number of columns that we have. That's why the space complexity of this one will be order of m into n, where m is the number of rows and n is the number of columns. Similarly, in terms of time complexity, that is also going to be order of m into n. The reason being is that we iterate through the number of rows and then we go in a nested loop for number of columns also. So this is m, this is m. So time complexity is m into n. And that's pretty much it. Thank you for watching. Please like and subscribe. Bye.